Today we are going to have a quick introduction to torchvision. So torchvision is a library that is built to facilitate research and experimentation in the field of computer vision. So torchvision is giving a lot of transformation and augmentation classes and functions that can be very well used in the training and the model building and processing and things like that. So here we have, if you look at different submodules, you can see for transformation and augmentation we got torchvision.transforms, and then we got models and pre-trained weights, datasets, utils, and so on. So I'll leave you to explore this one, but I'm going to give you a quick introduction to how we can use transforms, and I'll also look at the models. So here we have different models and pre-trained weights, different problems. So there's the classification problem and different pre-trained models that we have, AlexNet and so on. So ResNet, and yeah, a lot of them. And we also have different pre-trained weights. So this can be used for transfer learning or all kind of computer vision application building and things like that. So I highly recommend to go through this torchvision documentation and explore this yourself. So now let's just go to a kernel and look at what are the transformations and how can we use it, and let's just have a look at a couple of examples. So for this, I need to import the PL image and torchvision.transforms as transforms. So I have imported a dummy dataset. So you don't have to do that. So you can I just did it because I imported. So you can import any of the data images that you have to experiment on this one. So but ideally on training you'll have or a training pipeline. So I'll import this one. Let's import and we can look at the image that we loaded in, and then what we have is a function that I just want to show you, which is very well used in different computer vision problems. And we look at the center crop. If you want to let's just say this just crops the center of the image with a specified pixel value. So you can do this and you're gonna get the center 50 cross 50 pixels, and if you want, like, let's just say 200, and you can get the center 200 cropped and so on. And this is a class and we have to initialize it. So torch.transforms give you classes. So transforms.centerCrop has to be initialized, and so is all the other things that I'm going to explain. So if you want to use the functions, we'll go to that later. So horizontal flip here, this is the probability value. So when you have like multiple data coming in and you just don't want to horizontally flip all of them, you can give the probability of what percentage of the data needs to be flipped. Here I only have one data, so I need to flip it and show you. So I'm given the probability equals to 1, but it is something that you have to give like 0.3 or 0.4, something like that in the data set. So it's horizontally flipped from the original image. So then there's color jitter. This is some sort of a filter that we can give on top of the image. So given brightness, contrast, and so on parameters, so you can change the values of them and have different filters applied to the image. So yeah, let's just the color transformation you can see, and let's just say if we have saturation, high saturation, it's going to look like this. And another one is like a 5 crop, which crops the image into 5 parts, taking the 4 corners and a center. So with a specified pixel value, width and height. So you can do that, and it's going to give you like 5 different images of the specified size. Another important thing is how do we facilitate multiple transformations in a single transformation line. So this can be done using transforms.compose, and once we do this compose, we just have to pass in a list, and that list has to contain all of the transformation that we are going to give to the image. But one thing to understand here is, and be careful about this one, is when you look at the torch.transformation page, torchvision.transforms, you can see different functionality transforms on PL image and torch tensor. So this many classes can be applied on PL image or torch.tensor, doesn't matter what the incoming data type is. And some of the functions classes can only be applied to PL image only, and some of them can only be applied to tensor only. So you have to be really careful of that. So now if you want to give some of the transformation that's only allowed to a torch.tensor, then you must consider giving transforms.toTensor to convert the PL image into a tensor, and then apply. After converting that into a tensor, you can here do tensor only transformations, and just have to do it logically. And another thing that we can discuss is the functional alternatives of all of the classes. In certain situations, you don't want to instantiate the classes, you just want to have the extra freedom to use it as functions. So that's the reason why torchvision is providing transforms.functional. So once we import that, you can use later, previously we have done a transforms.toTensor. This is a class initialization, and here we can use the functional alternative of that, and it would look like this, and it's going to do the exact same transformation to the image. So this is going to convert the image into a tensor. So all of the transformations can be done like this, and you just have to refer to the torchvision documentation, and it's going to be very straightforward. And also we can look at center crop, and as a function it's going to work perfectly. So with an idea of what torchvision.transforms are and how can we do different kind of things with it, let's just dive into a project which is going to be facial keypoint recognition. So let's just get started. So welcome back to another video. Today we are going to go through some of the computer vision projects, and specifically we're going to look at facial keypoint detection. And today we are going to do this on Kaggle notebooks. And if you're not familiar with Kaggle is an online community for data science and machine learning practitioners. And you got several different kind of things on Kaggle, like you can participate on a competition or host a competition. You can contribute to data sets, and you can create different notebooks, and you can contribute to models, and you can participate in discussion, and it's totally, and you do have a couple of lessons and things like that as well. So you can, all in all, this is a complete package for if you are going to be a data science enthusiast or somewhere in that sort. So without further ado, we'll look at how we can develop this model. So today the dataset that we're going to use is facial dataset. So this dataset is very huge, and it's got like around 21 GB of data, and you can see like 52,000 images, and this is not annotated images, so we'll need to annotate this one. So I'm not going to demonstrate how we are going to annotate it, maybe in the end. But what we are going to do here is, I have annotated versions of this data which I have already created. So I'm going to use that thing and show you how we can develop a facial keypoint recognition model. So if the annotated data would look like something like this. So this data are essentially taken from there, but annotated. So annotated data, it's annotated on the image, and the coordinates are actually saved into another CSV file. So we get for every image the coordinates corresponding to different features that has pointed in this red label, and the corresponding coordinates are also something that we have access to because we annotated it. So I have created this dataset, and we are going to load this dataset. I have actually one more dataset, so this is like in two parts, dataset 1 and data frame, and the dataset 2 which I have already created. So I'm going to load that data, and let's just go to the notebook. So if you want to make a notebook on Kaggle, you just have to press create on the left, and you can start making like new notebook or dataset or competition. So what we are going to do is notebook in here. So the notebook also has several different features. So we can actually have a look at several different features that we have. I highly recommend you to go check it out and mess around with this thing. So we got like different accelerations, GPU and TPU, and we can schedule the notebooks, and we got Python and R language that we can use, and a couple other settings as well. So we'll go to those settings as we progress in the project that we are going to do. So what we first have to do is load in the data. So I'm going to load this data and this one, which is already something that I have prepared. You don't really have to worry about this one. It's loaded. Yeah. First of all, imports. We'll need to import torch. We'll need to import pandas. We'll need to import torchvision. Dot transforms. We need to import this is an image opener, and from torch data loader details dot data import data, come on, loader. And something that we did not import last time was tqdm dot notebook import tqdm. We'll need to import OS module. We'll need to import NumPy. Quite a lot of things that we are going to make use of. Import NumPy as np, like we have discussed in the last in the PyTorch intro video. For whenever we need to calculate the metrics, or if you want to do something with the metrics, taking metrics from the GPU to CPU, we're essentially going to use NumPy somewhere. Import torch. Okay. TQFM, no, it's TQDM. So we have, I think, some of the imports, major imports are done. So in this project, the as most of the projects in deep learning, setting up the pipeline is going to take 80% of the effort, and the rest of the 20% would take like making the model. And optimizing it is a different topic on itself. So we're not going to cover the optimization here. So we are going to develop a pipeline and we are going to train it. So the first part, of course, we need the data into a format that we can read into. So first of all, our data looks like, as I told, our data has like key points annotated on the image itself, and also the coordinates for every data is saved into a CSV file. So what we have is, whenever we take an image of a particular name, what we have is that image and the annotations on top of itself, and a CSV file containing its name and the annotations for different features and the coordinates of that annotations as the features in the data frame. So how we can do this thing, I'm going to import I'm going to take the annotations. So if I show you in here, we got in the first one, so we have a data frame. So this is the thing that we have with the real annotation coordinates. So annotations equals to pt dot read CSV of this. So the first thing that I would like to make is annotations could be, the columns could be annotations dot columns equals to I dot lower, because I don't like to deal with capital letters most of the time. For I in annotations DIONS annotations dot columns, and some of the columns, I'll guarantee you that some of the columns are going to miss some of the coordinates, and we don't want that. So for a complete training, we could either impute those missing values, or we can reject them. So in this case, a lot of the columns are not going to miss any values, so a couple of them could be. So we are going to look at annotations dot isNA dot sum. So not a lot of columns are actually missing, so we can actually remove these ones. So but before going to that, I want to show you what annotations look like. So these are what annotations are. So the features that we extracted are the coordinates of the outer left eyebrow, x and y coordinates. I mean, image is essentially x and y coordinates. So we want like different features like outer eyebrow, inner eyebrow, and outer right, different features corresponding to chin position, nose tip position, like right side of right corner of the mouth and left corner of the mouth, and different things like that. So the facial features, essentially, that's the reason why we call it facial key points. And once we annotate this one, it's just going to look like it is capturing the face, so different key points on the face. So once we train it, we should be able to produce and identify facial key points from plain images. So that's going to be effective when we want to detect a face. So that's the main motive of the project here. And as I said, we can annotations dot drop in axis equals to 0 and in place equals to true. And I need to make like a thing called selected images, because annotations first column is essentially the image names. So I don't want to take every image, so we have essentially dropped some of the image names here. So I don't want to take images that doesn't exist in the data frame, so I only want to take the images that are in the data frame and also in our data set that we imported. So I'm going to say like selected images equals to set of annotations img name dot values. So that's it there. And now we are going to define different data. So we got two data paths. So data path 1 and data path 2. And data path 1 is dataset 1, which is this path. It's got a lot of images in it. But some of the things that I'm going to do in this processing and setting up the pipeline is completely dependent on the way that I got the data. So you would have to customize it depending on how are you getting the data in. In a real world problem, when you are doing it, totally depends on how you're going to get the data. So once you get the data, you are going to essentially do the same pipeline, but it is going to have slight variations. So path 1 images. So I need to read the images in it, and path 2. So we got data path 1, data path 2. So data path 1 has like 900 and something images, and the other one has like 500 and something images. So I want to split those images totally into training and validation data. So what I'm thinking is my training data needs to have like at least 1200 data points. So that's what I'm thinking right now. So that's going to be a good amount of training data. Now the data set is only less than 1500 or so. So what I'm going to do is list of what I need to do first is os.list dar, which is going to give me the data path, and this is going to get the all the names of the files that we have in the data path 1. But I cannot take this data because this data contains data that are not in the data frame because we have rejected some of the data. So I need to make an intersection with the selected images and then a list of it. So it's going to be this. So at certain points, if your data is really overwhelming, then you're not going to be able to do this thing, because I am saving these names into a list just because I only have less amount of data. But if you have a lot of the data, then you would need to figure out some way to make this as part of your data loader, and that way you will not be consuming a lot of memory saving stuff into a list, which is a major thing when it comes to out of memory error handling in Python. Set os.list dar. I'm going to exactly do the same thing. Data path 2 dot intersection of and selected images. Where did I go wrong? Yeah. So once you're done path 1, you can look at the path 1 images. So it's gonna look at it's just a bunch of names of your images that are in the path 1 location, and path 2 will be the ones. So yeah, so from I'll take consume input from both of those paths, and then I'm going to get somehow 12,000 from both of this combined as training set and the rest as validation. So I need to make a class called config, and elements will get filled in this one. But for now I need to number of training samples equals to 12,000. I mean 1200. Num training samples is what I meant. Num training samples. It's really easy to have like a lot of typos in num val samples. Num val samples are going to be whatever left. So length of os.list dar. Did I write? Okay, list dar. I'm going to zoom in a little bit. Yeah, os.list dar of data path 1 and plus os.list dar of data path 2 data path 2 and total length minus number of num training samples. Train samples. Oh, sorry. So now I have to change it a little bit. So this is num training samples. So this is going to be exactly our validation number of validation data that we want. And if I want to, I can throw in like train sample size and train batch size and things like that. So later we'll come to that, but for now we'll label it like a normal stuff, or more general of items, and more training related items will be training related hyperparameters will be written in here inside the config. So I have explained why I am doing this config in the intro to PyTorch video. So make a list of training data. So for making a training data, what I need to do is train data list is going to be list of, I'm going to map. A map function is something that you can pass in a function which only takes one attribute and then an iterator. And what happens is the map function goes through the elements of the iterator, and it's going to apply this function, and the map function would return a map object, and I want to convert that into a list, and that's the reason why I've wrapped a list around it. So what I'm going to do is make a lambda function, lambda x, and os.path.join data path 1, and this is the only way we are going to be able to open things, because this data path 1 images and path 2 images, we got the names of the images only. So in order to open that thing, we need to join that with this base folder path. So the whenever we open the path, we will need to pass in would be something like this one plus the name of what we're going to do is path data path 1 comma x, and I'm going to pass in path 1 images, and this is going to be one list, and I need to take a couple other so this is the entire images that we got on data path 1, and this is going to be like something like 900 and something images. So I need to also get the rest of the data in the 1200 data that I need from the other folder. So that's going to be list of exactly the same thing, list of map, and here the folder name is going to be different, map lambda x os.path.join of data path 2 comma x, and here we got to pass path 2 images, and path 3 images that we don't want like the entirety of the path 3 images, so we want a slice of it which has to be until len of os dot list dir. This is just a simple math that I'm doing. Data path 2 minus data path 2 minus config dot num val samples, and the same would be going for this is train data list, train data list, val data list. I'll show you just if you don't understand it, just pause the video, and there are a couple of different lengths of the things, and everything is it's very simple mathematics. You will be able to do this thing. It's just I need to take like 1200 data, and one folder has like 900 and something data, and the rest of them has to be taken from the other folder. And once I take those images from the other folder to complete that 1200 data points, and the rest of the images will be treated as validation data. That's all. It's just as simple as that. Data path 2 comma os dot list list dir path 2 and x start join data path 2 comma x, and start list data path 2 and that of len of len of os dot list dir data path to minus config dot num val samples and to the end, and that's it. So now we'll oh sorry, so we got a typo in here, which should be a semicolon, and we got another, oh sorry, we shouldn't be having a semicolon here, and data a path. So there are a lot of typos in here. What you can do in Kaggle is like view and toggle line numbers is going to give you a line number. So we have had 3 typos. One was a list directory. In list directory, don't care about that. Another one was in here. So now what we have is train data list, which is the name of all of the files ready to be opened. So whenever we want to open it, we just have to pass in this path, and the image will be opened. And also in val data list, and you're gonna see, yeah, this. So we can inspect the length of it, and length is this, and that's the validation length, and the train length is 1200 as I wanted. So it's perfect. So next what we are going to do is make a data loader, but there are like multiple different ways depending on how creative are you with Python, and you can keep on making like different functions and things like that. Self data, and so what I'm going to do is for this one I need to, so the data loader has to give me the x's and y's. So x's would be the tensors. I would make the images into tensor, so that'll be a tensor, and there'll be a batch size. So let's just say I'm loading like 10 images at a time in a batch. So it's going to be a batch of 10, and the image is going to have like, there are color images, so the channels are going to be 3, and the image size is here for this data set, it's 512 cross 512, and I will take it as 512 cross 512, because if I reduce it, I might go into the danger of not capturing enough features or not being able to train all the annotated places in the data. So I'm not going to cut it or center crop it or anything like that. I'm just going to pre-process it, rotating and flipping it, that kind of, and that transformation also is going to be passed into the data loader. So these are the labels. The labels will be extracted from annotations, since the annotations data frame has the names of the images as well. So we'll search for the image name from the data frame, and once we get the image name, we got all of those features. We'll be extracting all of those features and changing it into some sort of a format, some sort of a shape specifically, and convert that into a tensor, and that'll be our output. So let's just do it. Annotations, comma, I need to have transforms equals to, I'm going to give this none for now. So if it's not done, we could at some point, this is always safe to do like none for starters, and we could also, so that we can also use the same data frame without using a transform. So self dot transforms equals to transforms, and self dot data equals to data, and self dot annotations equals to annotations. I think I spelled it correct, and if I have not, I'll come back and revisit later. Okay, and define length self and I'm going to return len of our data, self.data, and then define get item. I explained this one also the double underscore methods also in the intro to PyTorch video, where we have done the logistic regression, so I'm not going to explain in here. So get item self, and we need to take the index, so that's how the get item method works. And data equals to self dot data of idx, and so self.data is a list, and we are specifically extracting one of the items from the saving it to the data variable. And then we want labels, and labels is going to be self.annotations dot, I need to locate it by, I think I have spelled annotations correctly. Yeah, and locate, what we need to locate is annotations of img name, which is the column corresponds to the name of the image, and that equals to data. And if you look at the data name, so previously I've shown you the data name. So point is the annotations has a short name, which is going to be in the last 9 characters. So if the last 9 characters is going to, we don't want the extension of the base folder, so the last 9 character is going to be equals to that thing. We'll take the thing, take the image, and we'll extract everything except for the first column, which is the img name, which we don't want. We want all the other annotation data, and we'll convert this into NumPy, and we are going to reshape this into, and all of the data that we have is x and y data. So it's going to be x and y coordinates of the same feature. So let's just say chin x and chin y, and all of this data is like saved right next to each other. So what we do is we're going to reshape this into the number of features we have is, I think, around 60-70, something like that. I'll need to look at it, but we'll reshape it like this, and so that we'll have number of features in the x-axis and xy in the number of features as the rows, and the columns would be x and y feature of the particular feature, x and y coordinates of the feature. That's all. So it'll be something like, if I show you, it'll be something like a NumPy array np dot it's a tensor, torch.tensor of this sort. It'll be like this, and we'll have something like 1 2, and then we'll have something like 2 3. So this would be the features corresponding to, let's just say, chin. This and this should be a feature, the features corresponding to eyelids, something like that. And this is the x-axis corresponding to that, and this is the y-axis corresponding to that. So out of all the features, I hope it's like around 70 features. That is what we have extracted. So all of the 70 features will be somewhere in here, and x and y features will be like that. So that's the reason why I need to reshape it into -1, 2. So once we have extracted, and that's it, and we'll convert this into torch.tensor, and I want to specify d type equals to torch.float 32. Float 30. So d type equals to torch.float 32, and that's it. And once we have prepared our data and labels, what we need to do is like give a little transformation to the data. If transform equals to self dot transform is not none, what we'll do is image. Here we need to open our image. Image equals to image dot open. Yeah, we got an open method here, and open, and we just have to open the image. And once we open the image, we don't have the image, we have the data. So open the data. So this data will be open now. So image equals to self dot transforms I believe, yeah, transforms of image. Okay, and then we will return, I always want to return a dictionary, so that'll be easy for me to deal with it. So a dictionary of x is going to be like image and comma, and the y is going to be labels. Okay, and that's it. And since we have specified the transforms, we like to write what are the sort of transformations that we want to give. So image transforms equals to transforms dot compose transforms dot to tensor, and I'll convert this into tensor, and I'll also give maybe transforms dot just say random horizontal flip, and the probability equals to 0.5. This is all random stuff that I'm doing. So here the this p also can be treated as a hyperparameter, but I'm not going to do that now. Since we are not doing hyperparameter optimization, a lot of the things would be left as is, and all the important parameters that we would anyway give it in the config file will be given it in the config file. So keep an eye on this one. So I would also write it down in here, can be a hyperparam. Okay, and color jitter transforms dot color jitter, so brightness equals to 1. So all of these parameters, also contrast 0.2, and saturation, come on, saturation equals to 0.2, let's just say, and that's it. We're going to do train data equals to face data of train data list, and we need to pass in the annotations. Come on, annotations, and then we need to pass in image transforms. That's it. And for val data, what we are going to do is exactly the same thing, but here it'll be val data list and annotations, image transforms, annotations, image transform. Now what we need to do is the loader, train loader equals to data loader, and this data loader will take train data, comma, config dot something, data dot data config train data, and config dot train batch size is what we're going to do. Train batch size. Okay, but we don't have train batch size in here, so we'll need to do train batch size equals to, let's just say I'm gonna keep it as low, and val batch size also low. This is val batch size, and configure train batch size. So copy this one, and again, and this is my val loader, and that's going to take val data and val data, yeah, and val batch size. That is it, and we are done. We got something. Oh, compose. So compose, this has to be a capital, and yes, we are done. So we'll check it out and we'll test it. So what we'll do is next of iter of train loader of let's just say x. Oh, I was just not attribute annotations. The face data object has no oh, okay, face data is not defined. Oh, okay, this face data, now it's defined. Now again we got a problem that I misspelled annotations somewhere. So this is in 34. Tensor self dot annotations equals to annotations. Face data has no attribute annotations again on 34. And didn't I annotations? Yes, annotations, yes, annotations, and annotations, yes. And module torch has no attribute float torch dot float 32. Okay, this is all typos. So okay, now we are done, and we got the data and y also in the same shape, and dot shape it should be 5 comma around whatever 70 or whatever the number of features, comma 2. Yeah, 5 comma, we got 67 features and 2. And x, if you inspect, it's going to be 5 comma 3 comma, because it's 3 channels, 5 comma 3 comma 5 total. Okay, perfect. Now let's set model. This is basically going to be a lot of convolution layers, and then a lot of pooling layers and nonlinear activations. Probably we can use like ReLU activation. That will be it. And finally we will have some linear layers, and we'll get the outputs into the same size as the labels that we have done. So it's going to be like 67 start to output. That's it. So let's just write a class keypoint model of nn.module, and define nn self, and it doesn't take anything. We don't have to take anything. We can directly convolution, we are going to change the channel size, and we're going to put some stride and things like that. Okay, super, so referencing the supers class dot init. That's it. And let's try it now. I'm not going to keep this in a sequential term. Let's just also do something that's not sequential. There are multiple different ways you can actually write this one, but I'm going to go the I'm going to define every layer separately for clarity also. I just don't want to if it's the first time you're doing this one, then doing appending different layers into a sequential would not be very easy for you. So let's just go and look at each of the layers. So self dot, I'm going to do convolution 1. This is our convolution layer. So if you don't know what convolution or convolution action is or operation is, you just have to go to torch. Yes, here we got PyTorch, and go to PyTorch, and what you gotta do is torchvision. Oh sorry, you can go torch.nn, and here you'll have convolution layers and convolution 2D. This is what we're going to do now. So read this thing, and we got everything in here. And see, and this part is really important, and point is, once we do the convolution operation, our image, the size of the size of our image is going to be different. So depending on the height and width of the input image, let's just say 512 and 512 for our case, and for convolution operation we are going to use different parameters like dilation, kernel size, padding, and stride, things like this. So once we, for this combination, what sort of output image size is going to be expected is provided by this equation. So this equation is kind of important in the sense you had to understand this equation, and for the first couple of times, and then it'll start kicking in, and it'll be easy afterwards. And everything is actually given in here, so the implementation is also given in here, so you can read this part. It's a short part, but it's going to be really helpful. Okay, let's just go into, so convolution layer 1 is equals to nn dot convolution 2D 3,32, kernel size is going to be 3, stride equals to 1, and we give a padding equals to 1, x and y. So bias equals to true, and yeah, so now we'll do self dot ReLU of ReLU 1. That'd be okay. Self dot ReLU 1 equals to nn dot ReLU, ReLU in place equals to true, and we are going to give a self dot max pool, just say pool equals to pool 1. I given it like the first part of this sort of an operation, so we're going to essentially repeat the same operation again and again. And nn dot pool 1 equals to nn dot max pool, and max pool 2D, nn dot max pool 2D, and kernel size equals to what is my kernel size? Kernel size can be equals to kernel size equals to 2, and stride equals to it's going to be the same. Okay, so coming into the pooling layers, you'll need to look at the pooling layers and how it works, and this is just a max pool layer. So what happens is we are going to do a convolution operation, and convolution operation essentially take in here it's going to take 3 3 kernel, and it's going to stride stride equals to 1, so it's going to slide through the pixels that we have, 512 comma 512 pixels. And once we'll keep the kernel size of 3 and stride through it. So for every other pixel, not every other pixel, so every pixel, so the stride equals to 1, so it's every pixel. And finally we will give a padding layer, and the padding is going to be a single pixel throughout the border of our image, and that's it. And what we are going to do is an operation, and our kernel, the kernel that we initialize, is going to have weights, and we are going to compute essentially that weights into our pixel, and then we are going to that's our convolution operation. So the maximum operation would be max will look at a kernel size of 2. I mean, after the convolution operation, max will look at kernel size of 2, and it will just take the maximum value in it, maximum pixel from that particular image, or let's just say an image representation. Essentially it's just a pixel values, or a tensor, kind of a tensor. From that tensor it's going to extract the maximum value to tensor, and it's going to stride with every other pixel. So stride equals to 2. And now once we have done this, so also here the input channel size equals to 3, so this is the RGB input channels. So now we are going to convert this into 32 channels. As we do this thing, we are going to change the channel size as well. So essentially our picture is of 3 tensors of 512 and 512. So this is going to convert into 32 tensors of I mean, the shape is going to be changing. So previously the shape was 3 cross 512 512 for one image. So now it's going to be 32 cross whatever this is going to produce from the equation that I've shown you earlier, and this is going to be 32 cross some other shape, and after this stride it's going to be 32 cross a different shape. So if you don't understand this one in deep, for doing this one you don't actually have to understand this one, but for optimizing you will need to understand this one. So if you want to understand this one, I mean, you have to understand this one if you want to develop model for yourself. So go to PyTorch documentation, and you're going to get a good idea of like max pools. I have shown you like in the intro video. So self dot conv2, so convolution 2 essentially is going to be exactly the same thing. I'm going to do exactly the same thing, but with one difference is going to be the channel output channel size. So I'm going to copy this one and I'm going to edit it. So my conv2 equals to 32. I'm going to change it to 64, and kernel size equals to 3, and stride equals to 1, padding equals to 1, bias equals to true, kept in place. So nn.ReLU equals to self.ReLU2, and max pool 2, nn dot max pool of kernel size equals to 2, and the stride equals to 2. Now we're going to do this the same thing again once more. So it's going to be 3 convolution followed by max pool and a ReLU in between. Exact same thing, but this thing will be changing. 64 comma 128. Conv 3. ReLU is going to be in place, and max pool is going to be exactly the same. Max pool 3, but it's going to be max pool 3 and ReLU 3, max pool 3. So now I need to establish a fully connected layer. So because I want my output to be batch size cross 67 cross 2. So self dot fully connected layer 1 equals to nn dot linear, and 128 star 64 star 64 and this is going to be fighter, and my bias, I need the biases to goes to true. This fully connected layer essentially takes image, just say we got an image of size something in here. This is going to take, and it's got like 128 channels as well. So essentially this is going to create 64 into 64 of an image from at this point, and I'm flattening it. I'm taking like 128 into 64 into 64 and I'm flattening it and encoding that into the linear layer that I established, and that encoding would be to a 512 sized linear layer. So the output of this linear will be a 512 size. And so now what I've done here is, at this point our image is going to be 128 cross 64 cross 64. So it's a image of like a square image with 128 channels. So I want to flatten it and then keep it to this one. So the flattening point is not given in here, which we'll do once we do the forward pass. And here we need to establish this sort of a linear layer that encodes flattened pixels into 512. Why 512? I would that's just a number randomly assigned. You can actually assign this into like 1,000 or 10,000 or 100 or whatever the number you like to. But 512 is like a general number that I've given. So nothing special about that. So I need to give again a ReLU self dot ReLU here as well. ReLU 4, and ReLU 4 is going to be NN dot ReLU. Come on, ReLU. NN dot ReLU in place equals to true, and the final layer self dot fully connected to, and this fully connected to is the one that takes, now our pixels are flattened and we have encoded that into 512 length, and this 512 has to be taken in and NN dot linear of 512, and this 512 will be taken and I will encode it to 67 star 2. So 67 is our feature length. So 67 star 2 is going to look like a long random number, real numbers that we are going to generate, like 67 into 2. That's going to be that many. So what we are going to do is like 67. What we are going to do is like encode that into 67 into 2. That's the total number of variables that we want to generate, and later we need to reshape it for inputting that into a loss function so that our labels and output will be in the same shape. So bias equals to true, and that's it. Now we can write define forward function, and this forward function is going to be self comma x, and I'll say on one x equals to, this is going to be a lengthy and cliche part which I choose to write in this way. So you can write it much shorter ways, which is more ideal. And x equals to self dot convolution 1, and I would say x equals to self dot ReLU 1 of x, and again x equals to self dot max pool of x. Okay, so these are the three things. Oh sorry, max pool, I said pool 1. Okay, so these are the three things, ReLU 1, conv 1 and ReLU 1 and self dot pool 1. Okay, that's it. And we need to do this for 3 layers: convolution 2 and ReLU 2, and oh, I didn't say pool 1, and what's up, convolution 3 and ReLU 3 and pool 3. Okay, and finally we'll come into x equals to x dot view, and we'll view this as -1 comma 128, because at this point I have defined it like this is the shape, so I want to view the image in this way. So 64 into 64. So once we do this, we can do x equals to fully connected 1. So fc1 or self dot fully connected 1, I believe, fc1, yeah, fc1 of x, and we have viewed x like this, x is equal to, so then I'm passing it to the fully connected layer, and then we have again another ReLU self dot ReLU 4, ReLU 4, the final ReLU, which is a nonlinear activation. Z, did I give Z? Okay, x, okay, and finally we need to view this into give this into a fully connected 2, and x equals to fc2 of self dot, do not forget the self dot, fc2 of x, and finally x equals to x dot view -1 comma 67 comma 2. This is going to come in batches, so that's the reason why I've given it -1. So fc2 also settled. So now we'll simply return x. So this is our model. We'll do a couple of convolution followed by ReLU followed by max pool, and we did that 3 times, and we outputted that thing, straightened the image and outputted that, and encoded that into the dimension of 512, and then encoded that into dimension which is equals to the total number of features combined with the x and y coordinates of facial features, and then that thing is passed through a nonlinear activation, and then we are essentially reshaping it into look like our real output. And then we'll give that into the loss function, and we'll try to reduce the loss, optimize it, and finally we want the random numbers that we generate, and we'll back propagate and everything, and we want our weights to be in certain way that would optimize the loss function, and finally we'll learn to produce random numbers that are going to be around the vicinity of the labels that we have, which are nothing but facial encoded and annotated coordinates. Okay, now only one more simple thing that we need to do is define the model equals to keypoint model. That's it. It doesn't take anything. And so I need to before I go to that part, in the config I need to write a device. I need to write actually a whole lot of things in config now. So I will start by writing epochs equals, let's just say I'm doing 5 epochs, just randomly. So device equals to like we discussed earlier in the intro class, so CUDA if torch dot CUDA dot is available, come on, is available. So else we'll call, sorry, this is not a method, else we'll call CPU. So if this is true, then we will return torch dot then we will return CUDA, and otherwise we'll return CPU, which means either way we'll be able to train it once we run this thing. Otherwise we'll not be able to see. If you only give like CUDA, if you haven't enabled CPU, it's going to yell that you don't have a CUDA. So later we are going to give this an accelerator. So this is a good one. So we're going to use one of those, enable it and run this entire thing. So now we haven't run our function, so it's okay. Our thing is working. Keypoint model is working. And model equals to model dot to device. That's what I'm going to do. Model dot to device equals to this to function. You can see like the to function can take a lot of parameters. So if you want to convert something into a different data type, also you can give like dot to d type equals to something else. And here I'm using the device parameter, and I'm going to use config dot device. Yeah. So now our model is going to be, now it will be in CPU. So once I turn on the CUDA, it's going to be on GPU. So criterion is going to be nn.msc loss, and I need to optimizer equals to again I'm going to torch dot, this is your choice, torch dot optim dot rmw, and model dot parameters, and lr equals to config dot lr, which I did not specify. So I need to specify here a learning rate as well as equals to 1e, which is a -5 something, and I think that's it in the config file as well. So now I will move to training. So I think we have given it, okay, 1e -5. So now we'll do this part, config.lr. You don't have to do anything now. So what you need to do for epoch in TQDM, so something we want like a progress bar in range config dot epochs. So epoch in config dot epochs, what I'm going to call is train loss. So now for batch in train loader, batch in train load or s, batch in train loader, I think train loader is the name, and x equals to batch of x dot to device equals to we have the device config dot, which I'm going to copy here, and we'll need this. So y equals to batch of y dot to device equals to config dot config dot device, and output equals to model of x, and loss equals to criterion of out comma y, and loss dot backward, and I will do loss dot backward and optimizer dot zero grad, and optimizer dot step, stp, and we'll do train loss, something that we want to define in here. So train loss equals to this is going to be the average loss, train loss plus equals to loss dot item. We just want to take the item from loss, and once we have the train loss, after every after we once pass through all the examples in the train data, what we are going to do is divided by equals to len of train loader, and that is it. And point is, if you want to plot something, you need to output this into something else. So let's just say average loss train, or let's just say average train loss, and average valid loss, or val loss. And for now this is going to be just 5 epochs, so I can do this. And if it's not, then you'll need to do something else like memory efficiency and things. With the torch dot no grad, you get to wrap it around this one, because this is not going to use the gradient. This is out of the gradient computation loop. So whatever I write in here, so these operations are not going to be a part of, because I'm going to compute loss in here. So once I compute the loss, essentially if I don't wrap it around torch.nograd, that loss, the operations that I've done to compute the loss function is also going to be a part of the gradient computation when I come to training the next epoch. So that's the reason why we don't want gradients to be computed when we do validation. We just want to compute, I mean, for the model at the moment, because we have changed the parameters in the model quite many times, and so the model is actually a little updated now. So at this point we'll validate, passing all the validation data, and we'll output the loss function. So what is the loss that we're incurring in validation? That's what we want to monitor. So I'll also say val loss equals to 0. Essentially it's going to be exactly the same, but we will not be updating the gradients. Batch in val loader, it's going to be, for batch in val loader, we'll do x equals to batch of, again, x dot to device equals to config dot device, and the same way we'll do y also, and that'll be equals to y equals to batch of y dot to device config dot device, and output equals to model of x, and we'll have loss equals to criterion of output and y, and val, we have defined a val loss that plus equals to loss dot item loss dot item, and then we'll do val loss divided by equals to len of, exactly the same thing that I've done val loader. And now what we'll do is we need to print out or append avg average train loss dot append train loss, I think train loss, yes, train loss, and I'll copy once more, and average val loss dot append val loss, which is the average loss per epoch. And once we are done that, this is going to pretty much train it. And once we have trained it, I just end this cell in here. So this is going to beautifully train, hopefully, and it's going to give also that it's gonna also use a progression bar and everything. So I need to import. What I'm going to do is like plot the loss function. So matplot lib dot pyplot as plt, and plt dot plot. What I can do is range len of average train loss. That's what I think I define. Yeah, average train loss, and then average train loss, average train loss, and I'm going to give it like the lines, and I'm going to give it a blue color, or let's just say train loss equals to red color. And also I'm going to copy this one, and I'm going to give this blue color. And I made a mistake here. Average, it's going to be average values, average values. I think I don't have a typo. And also I'll do plt dot legend, and that'll be train comma val, or train loss comma val loss. I'll just say average train loss and average values, so it'll be more clear. Average values. So that's it. Now what we're gonna do is turn on the GPU and train this function. Train this. So how we are going to turn on the GPU is like accelerator. Just go select a GPU. Language is Python. Internet is on. You don't have to have any other settings. You just have to turn on the GPU. So if you are doing any pip install inside or something like that, you would need internet is on. But that's the default case, so you don't have to care for that. You can also have like an option to schedule this notebook for a later run. So you can use like different options. How frequent you want to run it. So it's going to, like, if you specify like daily frequency or like monthly frequency, it's going to automatically schedule and run. So that's that, and you got the freedom for that option as well, and a couple of different options. But now we have successfully turned our GPU on, and what we're going to do is basically run it, and we're going to run all of it. If you don't have an error, it's going to run smoothly, but if you have an error, we're going to debug it. Let's just see. Yeah, we have torch dot, and then have no attribute convolution 2D. I think I did not that's a capital. Yeah, that's a problem. I made here a mistake. It's C is capital. Some problem with capital letters. So since I made a mistake in here and I copied the mistake over and over again, so yeah, that's the reason why. Again, true is not defined, and that's in bicycles to true. Self-star FC1 self-star FC1 bicycles to true. Yeah, true is not defined, that's right. Let's just say config has no attribute LR. Config has no attribute LR. Oh, sorry, LE. So config now has no attribute LR. Config is not defined. So in 10, line number 10, I specify like, yeah, Anyway, and that's the reason why I copied config all the time. Yeah, that's a mistake. Yeah, capital letter. Two typos, and that's the reason why we got some bugs. And they were one was in here. So this was in to tensor. We so the autocorrect just did like PL to tensor, so that is being changed to tensor, which is the right transformation that we want to keep. And also another one is in here. So here just because we already had path 1 images and path 2 images, and these are the things we should be taken in here instead of reading in the dataset 1 and dataset 2 as we have done before. So that are the two changes that I've done now. So after 5 epochs it should return a model. And once it is trained, what you can do is two of the functions that I've written, you can try plotting the loss function, which is a way of looking at how the training went. So you can mess around with all of the parameters that hyperparameters that we have in here and optimize it. And once you have got the model, and you can also try to input another image and also the model, and then plot it on top of the image and look at how the key points are predicted. So that's it. So with this, we are going to wind up the session.